Hello everyone. It's today, March 17th. It's time. It's time. Let's do this. Alright, first of all, I want to check merge intervals. I don't remember I mentioned this from the past. Anyway, alright, let's take a look. What do we have today? Generate random point in a circle. Okay? So, given the radius and xy position of the center of a circle, write a function random point which generates a uniform random point in a circle. Oh, uniform. That is the point. Okay. Input and output values are in floating point. Radius and xy position of the center is passed into the class constructor. Okay. We have radius, center, and a y center. Okay. And a point on the circumference is considered to be in a circle. Okay. Random point returns a size 2 array containing x position or y position of the random point in that order. Okay, x and y. Random point solution. So we pass in the radius and the center. Radius and the center. Okay. Explanation. Input is two lists. The routine call and the argument. Solutions constructor has 3 arguments. This. The point has no arguments. Arguments are always wrapped with a list, even if there aren't any. And that's fine. So I have dealt with this type of problem before. The difficulty is to really make it random. Alright, so what we're trying to do is given a circle, so we already know the circle. How do we generate a random point? I mean, a random point. We can generate a random point in a square that's right. We generate a point in a square that is enclosing the circle. Does that mean the point generated will also be random inside the circle? I mean, another way to think about it, right? All right, I have 2 solutions. One is we simply generate points in the square that enclose the circle. That's just a uniform distribution from the distribution on the length and on the height of the square. So, let's go back to the sketch pad. So I'll kind of explain what I was thinking right now. So here's what I was thinking. Oh, they also saved my previous one. Can I delete it? How do I create a new one? I create a new, a blank. Oh, wow, that's how you do it. Okay, all right, so here's my idea. We have a system, right? A coordinate. Let's just, because it doesn't really matter where the circle is centered, we can always generalize in here. So that's a circle. Now we need to generate points randomly inside the circle. The one thought I have, is we create a square that encloses the circle. Now this should be enclosing, and then we can easily generate random points inside the square, right? That's just take a random value between here, take a random value in here, or uniform, and then that will be a point inside. Now once we generate it, we just run a check. Say like here, if a point, any point is here, we discard it. If it's inside, then we kept it. Because it's randomly, so if it's randomly distributed inside the square, it should also randomly distributed inside the circle. So that's one idea. Now another idea is, let's just draw it here. Same thing. Another idea is we have a circle, right? We use how do we call it? The radius coordinates. Is that how we call it? Radius coordinate? Is that how we call it? Uh, I honestly don't know how we call this. Polar. Yeah, polar coordinate. Yeah, we can do a polar coordinate, right? So polar coordinate, we have a random point on the length to the center, and we have a random alpha, a random point, a random angle. This one will work, I feel like, but I want to try both and just to see if I'm more confident on the polar coordinate than with this. Anyway, we are going to try both, that's for sure. I do not expect too difficult in the programming side. The programming side shall be very straightforward. We simply implement these two ideas. So there's no algorithm really involved. We do need to import random, so we're going to import random right here. I'm going to copy and paste this one in. There'll be no testing. Testing will be done just on that side. So basically, just self radius equals radius, self dot x center, self dot y center equals y center. Right? So this is the initial, and what we do is we always generate one that's based on 0, 0. And then when we explore the result, we just add this to it. Right? So now we have this. What do we need now is to create a random. Let's look into the random. I think Python random, they have random.random. Is that the one? Let's see, random, right? I know it's pseudo random. That's fine. We don't have to seed it. We just call it random.rand range. Rand in, no. Choice, no. These are all integers. Sample, no. Real value distribution. Okay, so this is a real value distribution. Oh, they have uniform. Oh, we'll have more. I have a Gaussian. Uniform will be sufficient. So we just do uniform. So uniform return a random floating point such that a to b and a smaller than b, b smaller than n, smaller than a for b smaller than a. Okay, so a touching, that's fine. Touching is fine. Oh, the endpoint may or may not be included in the range depending on floating point rounding. Oh, they use this equation. Yeah, okay, let's just do uniform distribution. So we're gonna say while true, x gonna be random.uniform, right? So a is going to be minus self.radius and self.radius, right? Y is going to be the same, exactly the same. And then we're gonna say if distance. Okay, distance. I'm not sure if Python might not have it, but it's fine. It's basically just x squared plus y squared. If x squared plus y squared is smaller or equal to self.radius squared, then we gonna break on this return. Return a list gonna be x plus self.x center and y plus self.y center, right? And if it's not, we just do it again until we find one. Okay, so this is our first solution. I'm afraid this one is gonna cost. We'll just call it r squared. Right, r squared, so we don't have to compute this every time. We compute it once. Oh, we actually do it here. Self.r squared equals this. So we compute it once, and then we don't have to compute it again. So we're going to do smaller equal to self.r squared. And then we're going to copy and paste this. And just to run it. Okay, let's see if it works. I mean, this one's not going to show me anything. It's going to be different. It's going to be very different. We basically are going to try it, see if this solution works. Oh, it works. Okay, so first solution works. I'm going to do some recording. Just write some comments. Take a look at the performance. That's all right. Only 8 test cases, so that's fine. So this is this solution generates a random point in the square enclosing. I spelled it wrong. Square enclosing the circle. We discard the point that is outside the circle, and return the ones that are inside. We also perform the point generation on the circle centered in the origin, and the resulting and the returned, and simply add the given coordinates of the center to the generated points when they are returned. So we just say it's running 148 milliseconds with a 53% ranking. All right, so that's that. And of course, we said we want to try another solution, which is using the polar. Now, with the polar, we have to do sine and cosine on this. So we have to search for math. Yeah, let's just do math. They have sum, GCD, power. We have to find trigonometry, right? Special constant. Did we pass it? Oh, here we go. In radians. So it has to be radians. So that's fine. So solution 2 will be using polar coordinates. So these are the same, and we don't have to do this. We can directly return. So we just say r equals random.uniform. It's going to be from 0 to self.radius, and angle equals random.uniform. It's going to be 0 to 2 pi, so 2 times math.pi. I don't think I import math, so I import math. And after we've done this, we need to convert them into x and y. I think, how do we convert? So x and y equals, x will be sine, right? X will be r times math.sine, sine A, y is r times math dot cosine a. Does it work on this side? I think it does. Sine is positive, cosine is negative. So, yeah, it works. And we're gonna return. We can directly return it. So I think, yeah, actually I don't think this is necessary. I just say return self dot x center plus, that's x, and here is self dot y center plus. And with this, there's no need to run a loop, because everything shall be included inside the circle. So this is the polar. This one's not gonna work. I mean, solution is not defined because I haven't turned it back to solution. All right, wait a little bit, run again. Maybe it'll work. All right, see. Submit. Pending, judging. Oh, it says no. Is this not random? Huh. I am surprised that it's not random. It's impossible to check this. Are you saying I don't know. Are we saying that this doesn't work? 0 to 2 pi, right? 0 to 2 pi, that's, we pick a random angle. I said I have high confidence in this, but it turns out this one's not right. And then from 0 to this, it's not? Or is it just the computation is not right? I mean, it should be right. I mean, if the r is radius, is now uniform distributed? Huh. That's interesting. Why is that not uniformly distributed? Think about it. Think about it. So what we're saying is we're going to pick a random. We're going to pick a random r. So we pick a random point angle, right? We pick a random angle. That's fine. And after we pick a random angle, and then we pick a random radius. And that is not correct. That is interesting, to say the least. I don't know. Or is that I cannot go to 2 pi because I'm including 0. So I should not including 2 pi. I mean, yeah, that's true. We actually have higher chance of this thing ending on 2 pi, which means we need to exclude anything that's ending with 0, right? Does that make sense? Like, is it like higher chance of something? I mean, does it have higher chance of some point gets? Now we know that it does have higher chance because we, from 0 to 2 pi, 0 and 2 pi, we're hitting those two twice, so there are more possibility of numbers ending on the x-axis. So that makes sense. So we can remove 0. So it's like not 0, but we include 2 pi, but no 0. And as it goes around, we have the distance, right? The distance. The distance is also a random value. We say as we go around here, and we get a distance, or this. So basically, we're saying at any angle, we have a uniform distribution of points along the radius. That's what we're saying, right? We're saying at any given angle, we have uniform distribution here. So at any angle, we have uniform distribution. At any angle, we have uniform distribution. So how is that not correct? So okay, we're gonna remove 0, right? We're gonna remove 0. We're gonna say while true, do this. If a is not equal to 0, then we return. Try this. See if this one gives you a better result. So we say we recognize that we are repeating on one part. So we're trying to correct ourselves by not including 0. And we try it again. Pending, judging. No, it still doesn't like it. Huh. This is saying like this one does not work. Yeah, this is basically what it's saying, right? It's saying that this does not work. Very interesting, very interesting. I want to see if anybody talk about it. Yeah, to hang on to this thought, let's go to the discussion, and because I cannot figure it out. I mean, this is definitely one of the concern, but apparently it's. I mean, the only thing I can think about is because it radiates out, right? That's what I'm thinking, right? So you have, say, we have random points along this, right? Random points along this, and then we also say generate here. So we have random points along this. And because as it goes out, we can see there's more space here compared to space here. Maybe that's the reason, because there's always going to be more space on the top than the space at the bottom. So what we can say is this scheme will always generate points with higher density on the shorter, right, on this region than on this region, right? Which means if we really want to use the scheme, we have to compensate. We have to compensate for the density of points on like closer, as it gets closer to the edge, we have to compensate for the density. How do we compensate for the density? I mean, we can compensate for density. I don't know. I don't know. Do we sample more points up top? No, it's not. It's more. It's like for each unit. Like, can I delete? Clip art, star, crop, select. Right, can I select? Oh, I can. Well, let's just delete everything and try it again. So, we don't want this. Paint into layer. No, we just want a good old simple thing to work with. So this is a circle, right? So what this is for each unit angle that we select, right? So the first angle is here, the second angle is here. So for each different angle we select, and then we select a point, right? We say a uniform distribution of point along here and along here, that we can say that the points are more close to each other in this region compared to this region. Therefore, they're not uniformly distributed overall on this on the surface of the circle. Okay, that makes sense. That makes sense. So I think that's why it doesn't work. So can we find a way to still use the scheme, but like say compensate for the lack of density in this region? Compensate. I don't know how to compensate. It's like as we get higher and higher, we need to I don't know. I think just the polar solution is not going to work. All right, I'm going to call quits and take a look at how other people think about this problem. I mean, the solution one is the easiest. Basically, just blast. You blast it onto a region that contains a circle, and then since the blast is uniform, and everything will be uniform. I might have done this before. I don't know. Take a look. No, it's my first time. Yeah, I think that's a good question. Polar coordinates. You can. Okay, so you can do it with polar coordinates. Yes, this is the one I was doing. The point is that we should not use rand land times. Okay, that's what I was using. Okay, we should not do it this way. We should use SQRT. Huh. Why is that? Why is that? How the PDF and CDFs are obtained. All right. All right, as an easy proof, sample probability proportional to this. Oh, so it's proportional to pi r squared. Proportional to pi r squared. Okay. R should be proportional to r squared. That's true. Replace r with SQR. It should be proportional to r. R can be sampled by rand, and that's why we apply another SQRT when sampling. Be the square. Okay, x is twice as likely to fall between 0 and 2 than between 0 and 1. But if x falls between 0 and 2, the corresponding circle has radius of 2 in the area of 4 pi, while a circle with radius 1 basically has to cancel the effect. We need to take the square root. It is using this. Okay, let's keep reading. I mean, the code is not difficult. It's just the understanding of. Oh man, this is slow. The website, the page is 10 years ago. No wonder. I doubt it can even. Okay, so the basic idea, I think, is that what we're trying to do is to find the distribution that is pi r squared, all right? So we need to find a distribution that fit into pi r squared. This has to be a random point, which means it has to hit every point that's the area. right? So which means our probability shall be proportional to pi r squared. And now what we have is, oh, I think what they're saying is we just use the polar coordinates to find x and y, right? We use the polar coordinates to find x and y, which means x and y shall also follow. So x is equal to r. No, that's y. R cosine alpha, and y equals to r sine alpha, right? So with this, we say x and y, x is relative to r, and y is also relative to r. But eventually, we want x and y to be relative to r squared. Shouldn't we like square them? Why is it sqrt instead of square? All right, here we go. All right. Blah, blah, blah. Naive solution is to pick a radius uniform, yes, and then angle uniform, yes, but you end up with an excess of points near the origin. Yes, I think that is. We have identified that as well. This is wrong because if we look at a certain angle interval, say theta plus, yes, then there needs to be more points generated further out. That's true and close, yes. But one, oh wait, hold on, what is this? The radius must not be picked from a uniform distribution. Yes, the radius should not be picked. It should be picked more often further out and then close in. But one that goes PDF of r is 2r divided r squared. Huh? What is that? Why you have to pick it this way? Let me write something. I might have some idea. So yes, that's a correct observation that the radius has to be picked with a different distribution, right? So which means we're gonna pick points close to the origin, close to the center with less frequency than we pick outside, and it has to follow the line. So which means the probability have to be okay, let's take this part and then we just say, which means what we want is as we go out, like every time we go out, we'll have the same probability, which means the space, the area is the same. So if we're given a slice, right, and then we're given a current, let's see, this is R0, right, what we want is, let's actually go from the center, so it'll be easier. So it'll be delta R is here, right? So basically this is alpha, right? So we say pi delta R squared pi this times alpha divided by 2 pi shall equal to, if we move out another delta r, shall equal to pi 2 delta r squared, right? Times alpha divided by 2 pi. So this is the bigger one, and minus pi delta r squared times alpha. So that's what we want. And we can cancel out the pi, so pi can be canceled over here. So we have a delta r squared alpha equals, this is actually 2 delta r squared. So this is 4 delta r squared alpha divided by 2, so it's 2, which means what we're looking at, right? What we're looking at is, oh, that's actually not delta r. So first is r, and this is delta r. I want to do it again. This is delta r. So we have r squared alpha shall equal to, this is r plus delta r pi squared times alpha divided by 2 pi. So the other thing is the same, so like this, alpha can go. So we have 2 r squared equals r plus delta r squared, which means r equals r plus delta r. So we say delta r shall equal to this r. So we should follow this, right? This is what we're trying to do. We should follow this. But this is like different from, which means for every time we increase on the delta r should be square root 2 minus 1 times the current r. How do we reflect in the probability? Right, the probability means I don't know. R equals r times square root random. Now this is not clear. I'm still I like intuitively I understand it. However, I don't understand it very much. Somebody shared something else. Take a look. Okay, so yeah, this is wrong. Okay, so this is explanation. It's uniform. Okay, very nice. So read it. Yeah, we understand this part. Let's just see how can we achieve this? Yeah. Of area of circle rings, okay. The area of the circle with radius d that's true. And the area of circular ring between d and this, yeah, that's true. Which makes 3a. Similarly, the 2 with 5a, okay. From this, we can deduce that for increasing distance from the radius, the area is linearly increasing as this below. You sure it's linearly increasing? We can probably find the relationship between, yeah, we can try to find that. Okay, since the area and density of points, yes, in a circle ring is inversely proportional, the probability distribution of the distance from the origin should be linearly increasing between 0 and r to compensate for the reduction in density. Yes, since the area under the probability distribution function should be equal to 1, the PDF function becomes where A to be found. Hold on. What is this? 0 and R to compensate for the reduction. So this one, right, the distance from the origin should be linearly increasing the probability distribution. Yes, the probability distribution. So are we saying that we know that the probability distribution, the PDF, yes, the PDF shall be higher. Okay, I got it. The PDF is equal to alpha times R, because we're saying that the probability should be increasing linearly. So we do integration from 0 to R. I mean, it's 0 to R, yes, so 0 to R. So alpha R dr, it should be 1, and this one is alpha R squared over 2, just R equals 1. Right, so we know alpha is 2 divided by R squared. Okay, that's true, 2 divided by R squared. So we got a PDF. So the PDF of R, of sampling the R, is 2 divided by R squared times R. Okay, I got here. That's true. Cumulative distributed CDF can be found by integrating the PDF, and we can get this between 0 and R. So to obtain probabilities, we can utilize built-in functions. However, recall that we have only access to uniform random. Okay, in this case, we can use a random number generator to get a random number to mimic the CDF value of a random distribution of a random distance. In other words, for the CDF, we obtain a random point on the y-axis of CDF, which is always between 0 and 1, and then map it to the distance from the origin on the x-axis. This can be easily achieved as we know the analytical formula. So R equals R this CDF equals R this random. So we also need to use the CDF. Why do we need to use the CDF? CDF is a cumulative, right? Because the uniform distribution can be think of as the cumulative distribution. The cumulative, because we're doing from 0 to 1, right? From 0 to 1. So basically, because this is just the y-axis, right? This is the y-axis. We want to pick a random number on here, and if we project in here, and then we can know what R it is. Well, that's smart. So we need to do the PDF. So it's 2R squared R dr equals, oh yeah, it's R squared over R squared. Is this. So we pick a random value from 0 to 1, right? And then we're projecting, which is, that is correct. We utilize it and we get the result. Uniform is evidence. Oh yes. Can I like this one? Yeah, it's pretty good. Oh, I have to log in to like it. That's fine. Okay, that's a good one. That's a very good one. Now we know. Yeah. Very good explanation. Explanation of the article. That was in 2018, a long time ago. All right, so we know. Go back. As graphs. Take a look at another one, another two, and that's a good question. I want to take a look. I think there's probably one say we don't use SQRT. My first solution doesn't use SQRT, right? Anyway, let's take a look here. Wrong, yeah. And finally here is math.sqrt. Now the solution, the right solution is to use as in the number of points should be proportional to the area, and the latter is proportional to square root. Hence, our math, make sure, is uniformly distributed. Huh. Well, that's true. Get a random point. There's a new equation, random times r squared. Okay. Then we can transform it to the polar coordinates. Oh, that is even better. SQRT random, yeah. This is better. Yeah, I like this one better. Area is this. R is now I like the explanation. Oh my god, the drawing. Theta is quite obvious. We do uniformly. Probably more points. Okay. Yeah, we don't need to see. We know. Is probability density. Yeah, we have to do this. Is equal to, okay, let us define FR as CDF for radius, okay? Position probability to get between R and this is equal to this minus this equals FR. FR is probability density function, okay? So probability to get this small region is this times d theta. Yes, that is a yes. From the point of view, area of this region can be calculated as this d theta equals, okay, from here we get f, so we get the s. Oh, yeah, you do get it. You can get that it's increasing the probability, some constant c. Now this equals this, so this one equals this one. Yeah, now the question is how you generate data. So you can function this. After this inverse transform sampling. Idea is given uniform distribution, data from any distribution. We need to generate R from a uniform distribution and apply. So we have, yeah. Yep. We can do it rigorously. We can do it rigorously. Tool of accounting. Random number generator. Sure, that's random. The randomness, you can never be sure. I mean, how can a judge know the solution is uniform? In every language, I guess. We have to check the results. checks distribution. Points and got wrong answer. Do not specify what kind of distribution should be. Into several parts, split with degree, and then calculate the areas, probability on the points in each area, then you'll get a degree of confidence. Anyway, that's it. That's our excursion into it. So I'm gonna write this. I mean, the writing is easy. We just do sqrt on this. We do math.sqrt on this. And we don't need this. Yeah, and we don't need this. I think we just do this. This shall pass. Oh, did I close it? Man, I closed it while I haven't even finished. Oh, where's the problem? Problem is here. Oh, it's not a 1. Come on. Let's come here. Go back to the problem, to the submission. Let's try the polar again with a sqrt. This one shall work. No, this one's still not working. Why? I did this QRT trick. Or hold on. So what we're saying is, oh no, not here, man. It's not SQRT here, you dummy. It's SQRT here. That's math.sqrt on the radius itself. This one shall be right. This one is still not right. Oh my goodness. SQRT on the radius is also not right. How so? Isn't that the solution? Hold on, what we know is we know the CDF is R squared divided by big R squared, right? Which means if we want to generate a random number 0 to 1, right? We projected it to it. It needs to equal R squared. So it's R squared times this equals R. So it's okay. Let's do this again. I think it's math.sqrt, right? Math.sqrt and random that times R, self.radius. All right, let's try this one. This one shall right. Come on. Yes. This one's correct. Has to be following this. Alright. Alright, I'm going to redo the math proof, but I'm not going to waste your guys' time. So I'm going to just end it right here. And this is a good problem. It's a good math problem. Kind of bring back a lot of memories in that. So yeah, that'll be it for today. I'll see you guys tomorrow. Adios.